All right, guys, in this section, we will go ahead and finish up 7.1 and take a look at some initial value problems. So let's actually start with an example of why we need to do this. So if we're talking about finding an antiderivative, we might have something like find the antiderivative of 3x squared. And what we did, sometimes we called this little f of x, and then we called our antiderivative capital F of x. And in this case, our antiderivative is x cubed, and then the family of antiderivatives that we want to talk about is x cubed plus c. So sometimes they'll even say, find the family of antiderivatives, like this. Okay? But what we want to say in this case, if we visualize this, is that think about if your constant is 0. That's your x cubed. But let's say you have a plus 1, which is not necessarily a scale, or even like a minus 1. Well, if we take a look at a specific point, let's say right here, and we go down, we've drawn this well. Notice the slope, if I'm thinking about just going down vertically, I didn't line those up perfectly. I think I didn't line these up very, very well in terms of drawing these. But the idea is, if we're going down, the slope is the same. It's just a vertical shift, no horizontal motion, just vertical. And our slope is preserved, just our position up or down is what's changing. So this helps us understand why we have a family. And if I want the antiderivative, the one antiderivative, we need more information. So a lot of times we might hear the terminology initial value problem, where they are specifying a specific point that we have to have on our function. For example, let's say our particular function has to go through the origin in this case. Well, if we have to go through the origin, only one of our x cubed graphs is going to do that. The one that's positioned correctly so that it hits the origin. Right? If we are shifted over, well, now we're not exactly x cubed. We might see something like x minus 1 cubed, which isn't going to give us the same thing. But the idea of x cubed versus x cubed plus 1, this guy goes to the origin, that guy does not. So let's take a look at some wording that we're going to see to give us this sort of scenario. So I ended up picking this wording from your book because it's a little bit different than I might have phrased it. We don't want to get tripped up with what's existing. So for this one, it says, find the equation, switch to black there, find the equation of the curve whose tangent line has a slope of f prime equals, and here's where they're going to change. They're going to give you a function right here, right? It might be something like 3x squared or something different. So let's say in this case, our slope f prime of x equals x squared. And let's actually make it a little bit more complicated. Let's make it x squared plus x. And passes through the point. 0, 5. So in this particular case, what we want to think about is we're trying to find f of x so that the derivative is x squared plus x. That's another way to say it. And think about this. If your function or your curve passes through 0, 5, what that's telling you is f of 0 equals 5. Now, let's take a look at how this is going to work for us. Think about if we're given a derivative and we're trying to find the function that gave us that derivative, that's just asking for an antiderivative. So our first step in this case would be to find our antiderivative. Find the antiderivative of the derivative function or of the slope function. You don't necessarily need a parentheses in this case, but it doesn't hurt. And think about how we could break this one up. The antiderivative of x squared is x cubed over 3, and then x squared over 2 plus c. So what this is telling me is that this is the form for my particular function. It's a cubic, and it has to be x cubed over 3 plus x squared over 2, and then we could have any constant we want. But the constant that we pick has to be chosen so that 0, 5 is on the curve, or so that f of 0 equals 5. So what we want to do is go ahead and say this is telling me my f of x function, but now what I have to go after is c. We want to find our c. Then we'll have our completed function. So let's go ahead and jot this down and move it to the next page here. And then let's use the f of 0 equals 5. If you do f of 0, that would plug 0 in here, here, and then you still just have your constant. So in this case, f of 0 is going to give us c, and then that f of 0 is supposed to be 5. So this is actually telling me c is 5. Now, what if it was not f of 0? If you had something like, for example, instead of 0, 5, we had maybe had the point 1, 2. This would actually be quite a bit harder and maybe some messier fractions potentially. In this case, we would have plugged 1 in instead of our x. So 1 cubed, which is 1 over 3, plus 1 squared, which is 1 over 2, plus c, and that should have given us 2. So in this case, in the case that I gave us with f of 0 equals 5, c equals 5 quickly. And we could actually go ahead and write that our function was x cubed over 3 plus x squared over 2 plus 5. Then in other cases, if you're not given the x value is 0, you're going to have to work for it. So plug in your 1 for your x. If it were something like plugging in 5 for your x, now we would have to cube and square and put those over our 3 and 2 respectively. So you can see that this sometimes can get a little messy. But when we plug in x equals 1, I'm going to go ahead and just write our cubed and squared just for those of you watching later. This actually gives us a way to get c. So we've got to do some fraction math, some common denominators, but we could think about solving for c. So think about 1/3 is 2/6, 1/2 is 3/6. So this is really telling me that 5 over 6 plus c is going to give me 2. I could represent that 2 as 12 over 6. So it looks like c should be 7/6. Okay, so in that case, we would have the same base function, x cubed over 3 plus x squared over 2 plus 7 over 6. Okay, so in this case, again, this was using, instead of 0, 5, using 1, 2. All right, guys, so the only other types you're going to have in this particular section are ones dealing with applications. And sometimes they will give you a rate of change function. When they hear, or when you hear the words rate of change function, what they're telling you is, hey, here's what the derivative is. And then to find the original function, you can find the antiderivative. Other places where we've got some specific application that we've talked about already is position, velocity, and acceleration. We talked about the relationship between these derivatives. So the idea is if you differentiate position, you get velocity. Maybe I should write it like this. And a lot of times instead of a dx, they'll use a dt, like respect to time. A lot of times when we wrote this earlier, we just said if you differentiate, kind of like this. But the derivative of position with respect to time gives you velocity. Therefore, the antiderivative of velocity is position. Then, if you differentiate velocity with respect to time, you get acceleration. So velocity is the antiderivative of acceleration. So if they give you a acceleration function, you can find the antiderivative, and that's the velocity. They give you the velocity, the antiderivative is the position. Whereas if they give you the position, you can differentiate to get your velocity. So that can get a little tricky because you have to think about what are they giving me and which direction am I going. All right, guys, so take a look at this application problems. Let me know what questions you have. When we move on to 7.2 next week, 7.2 is going to give us some more techniques for anti-differentiation or integration, and we'll also take a look at some more specific word problems. All right, so that is it for now.